Okay, the long-awaited antiderivatives. So those last two sections, we talked about the concept of an integral, which is the area under the curve, right? In that 5-1 and 5-2. Now we're talking about an antiderivative. So we're getting more along the lines of what is the process? What is the rule that we go with? I'm not just looking at a graph at this point, okay? So let's talk about what this is. If I have f of x is equal to 3x squared plus 2x minus 7, and I want to take the derivative of that, right? So I take my 2, bring it in front, gives me a 6x plus 2, because we know the derivative of a constant here is 0. So this is my derivative. When you do an antiderivative, then we go back the other direction. All right, but look at what happens here. I can't go back the other direction. I don't know what this minus 7 is. So here's how we work with that. All right, because your constant becomes a 0 when you take the derivative. So because your constant becomes at 0 when you take the derivative, we have to account for that when we do an antiderivative. Because I don't know what my original function is, right? I don't know what's going on there. So we account for that. With putting a plus c at the end. That's my constant. So putting that plus c in there tells me, okay, I am taking this antiderivative and it could have a constant there. I don't know. So I'm going to put a plus c, right? If it didn't have a constant, and when we do our initial value problems and we see that there was nothing there to begin with, that's fine. We'll determine that c is representative of 0, and that's still okay because that's still a constant. All right? Okay, now let's look at a couple more notation type of things. This elongated symbol is called an integrand. All right? Just so you know what the words are, it's just that elongated symbol here for the summation. We've kind of introduced that already. And so I have 6x plus 2 dx. Now, didn't we have something that we did in that last chapter? That, ladies and gentlemen, is a differential. This means I have a derivative here. This is actually a derivative with x as the variable that I'm focusing on. You have to have a differential. There is always a differential. Always. All right? And you have to have this. So you have to have this differential that is in there. So make sure that you are paying attention to that whenever you work those problems. Sorry, my phone made a noise there. All right? That's important. Now, let's get into this a little bit more. There are different rules. Just like we had derivative rules, there are integral rules. And we're going to hit the highlights here on these. There's not as many rules for integrals as there was for derivatives. Our first one, however, is the power rule. This is your go-to rule. If I have x to the p dx, right, because that's my variable. Remember when, I'm going to squeeze this back, we took our derivative. What did we do? We brought it in front as a multiplier, then subtracted 1. An antiderivative is doing opposite of everything that we did. So for your power rule, we're going to have 1 over p plus 1 x to the p plus 1. And then, of course, that plus c because I don't know what else is happening, right? So instead of subtracting 1, I'm going to add 1. Instead of taking this and multiplying it in front, I'm going to take it and divide by that. All right? So everything that is opposite, that's what we're doing here. Okay, and we're going to practice these enough, and then we'll be going through it. Just like you did with your derivatives at the very beginning. You had to practice those to get good at it. We're going to practice these, and we'll get good at it. Here's another one. Constant multiple rule. We have the integral here of c times my whatever function it is that I have, right? Just like with a derivative, you can take this c as a constant and just leave it in front. You can take this c out in front of your integrand and then do your antiderivative. All right? So anytime you have that constant that's just multiplied, you can chuck that thing in front so that you don't have to mess with it and then just multiply it by at the end. Okay. Also, there is the sum and difference rule. So with our sum and difference rule, it's the same, again, I mean, these are all related, right? So the whole point of this is the fact that it is f of x plus or minus g of x, and in my integral here, dx. These are all related to derivatives is what I was spitting out. So I don't know how to say this. Limits work their way into derivatives. Derivatives work their way into integrals, which are antiderivatives. So remember how we never split those up independently whenever you do your integration? We're not going to now. However, here is the rule. I can look at each one of these pieces and break them into their own integrand. However, I'm even going to write it on the paper. Don't do this on your paper. We're just know that this is the rule so that we can break this up of what we need to, right? But we're not going to put that on our paper. We're just going to take the antiderivative of each piece. For instance, if we go backwards like what we just did on the problem that we had, if I want to integrate this 6x plus 2 dx, that's what we're going to do. So you've got your x here, and then I'm going to have this as my exponent of 1. I'm going to add 1 to that, right? And then bring it in front. So 6 is already there, but whenever I take this 2, then I bring that in front. Oops, I got a little excited about that, didn't I? I bring it in front, and then this is also my 2 because I'm dividing by that. Add 1 and divide by it. And then I'm going to have plus. Same thing is happening here. This 2 over here is like x to the 0 because there's nothing there. So if I have x to the 0, that's like a 1. But if I add 1 to that, so then that puts me here at a 2. And then I've got x to that first power, and I can basically divide this by 1. And then you've got your plus c always. It's an indefinite integral is what it's called. If there are no bounds, which we will talk about next, we haven't talked about that yet. If it's just an integral by itself, it's called indefinite. And then you just write it like this. Then you just clean it up. So I've got 6 divided by 2 is a 3x squared plus 2x plus c. Now look at this, 3x squared plus 2x plus c. I'm going to go back, look at the beginning of this. 3x squared plus 2x, and I didn't know what this constant was, so that's now represented as a plus c. All right? All right. Now here's caution, wee, wee, right? Notice this. There is no product rule, no quotient rule, no chain rule. When we are talking about integration, there is no product rule, there is no quotient rule, There is no chain rule. So there is no way for you to do that in here. And whenever you integrate, you can take the derivative that way. There's derivative rules for those, but not integration. You have to get everything in terms of plus or minus to use the power rule. For now. I'm going to say for now. Because you don't have to have that for every integration ever. Calc 2, a third of the class is integrating. All right? So we're going to come up with a whole lot of fun ways to integrate in Calc 2. For us, our intents and purposes right now is we want everything in terms of plus or minus. So remember how I harped on you when you were doing derivatives? Saying break this down, algebra first, algebra first, algebra first. Right? I was like a broken record. Welcome to the reason why you had to do that. You don't have any other choices. You can't just do a product rule or a quotient rule. You have to algebra first or you can't integrate. All right? We are going to learn about something called the chain rule here in a couple of sections. So we've got that. We'll have that going for us. Otherwise, you've got to algebra this thing down so that it's something that you can work with. Okay? Okay, we're going to do some examples here next.